Okay.
Go ahead.
So welcome to this new section of our first circle workshop. The next speaker of today is going to be Professor Driggs Campbell from University of Illinois, Urbana-Champaign. She obtained her PhD in Berkeley in 2017, and her research area is robotics, human-computer interaction, and machine learning. Please start when you can.
All right. Well, thank you. So yeah, as was said, my name is Katie, and I'm really happy to be here, and I'm very excited every time I get invited to these sorts of things because it's fairly different from what I normally think about, and so I get to learn a lot. So today, I'll be talking about mixed autonomy in a slightly different context. So usually when I think about mixed autonomous systems, I think a little bit more about the agent interaction. So thinking about how we can model those human behaviors, how this relates to autonomous vehicles, and how we can both design those models for autonomy and sort of leverage both of these insights and fields together. So we'll be talking about sort of this lower level sort of human autonomy interaction. And today, most of the work I'll be presenting is done by Yuan Shen, who's a CS student here at Illinois, and Masha Itkina, who's a nearly PhD student from Stanford, who I started working with during my postdoc there. All right, so my title is a little bit silly, but we'll kind of lean into this. So here's an example of a canonical or a very well-known example of poor vehicle pedestrian interaction. And yes, it is a little bit silly. I think it does capture a lot of elements of human behavior that are very important when we sort of think about how to design these systems and the impact of humans and autonomous agents interacting. So first off, if we just sort of take a step back at the very initial part of this scene, we can sort of see that Dustin Hoffman here starts sort of walking and crossing the street. This does represent or kind of show a key part of human behavior, and that's that most motion or most things that we do are guided by intent. So there's this aspect of sort of goals or underlying things that we want to do, sort of the semantic sort of high level actions that determine our motion and how we go about achieving them. The next thing is that attention becomes very important. So human attention basically determines how we're perceiving the world, and this directly impacts, the downstream task of determining our decisions and then motions and whatnot as well. So in this example, we sort of see two types of attention where we sort of see a failure. So first, we do see Dustin Hoffman where he is not checking both sides or checking the street before crossing the road. So in his view, he doesn't sort of see that this taxi is entering. From the taxi's perspective, they don't see the pedestrian. So in both of these sort of agents, like I said, these sort of representations or understanding of the world, we kind of have this mismatch here. So kind of understanding how we're reasoning about the world becomes very important for understanding the underlying decisions that are made. Sort of related to all of these, there are a bunch of hidden states that we can't necessarily observe, but we as people infer all the time. So for example, when we're watching this scene, we can tell that these two people are in this sort of heated conversation. They're both a little frustrated. Maybe this determines sort of what they are going to pay attention to. And clearly we see his anger there in the end. But they're basically a bunch of hidden things that are very hard for our intelligent agents to really start thinking and reasoning about. But we as people, again, we do this all the time and sort of make these sort of sequential reasoning, steps of reasoning to see how that sort of infers things downstream. The final thing I'd like to sort of point out is that communication is very key. In this example here, we see some very explicit communication with both, I guess, verbal communication as well as some physical motion. But when we really think about transportation and some of the communication that goes on there between agents, basically none of it is verbal. There's a lot of these sort of nuanced and sort of cues that we take, and sort of preserving this sort of communication becomes very important as we think about designing these systems. So these are sort of some of the key things to think about in this context of behavior modeling, sort of expanding on this. My group has looked at a bunch of different sort of pieces or facets of these. We've looked a lot at modeling human intent and motion prediction. We've more recently been looking more explicitly at driver traits, so trying to understand sort of some of these hidden parameters that determine, again, whether or not an agent is going to be cooperative or not. This becomes very important for things like downstream tasks, like when we have sort of complicated intersections that we're trying to navigate through. So having this sort of agent level understanding becomes very important. We've also been looking at I've labeled it here models for inference, but you can also think of this as inverse models. So this is models where we're trying to think about causes of behavior. So not necessarily just thinking about what the agent is going to do, but what is it that made them do it. And finally, sort of the more classic, I guess, view of things is, oh, it looks like that video is not playing. Pretend you see someone texting while driving. The more classic view is, or one of the original views is looking at driver monitoring. So really looking in at the drivers. So we've looked at these sorts of human models or behavioral understanding across many different sort of modeling perspectives and also many different levels of autonomy. So a lot of these approaches can be used for different things in different sort of contexts and whatnot. So today we're going to talk about these latter two. We'll spend most of our time talking about models for inference, and we'll touch a little bit on some work that we've been doing recently, driver monitoring, if there's time. But yeah, so we'll be focusing in on this idea of inference. And one of the things that I think is kind of fun about this project is what we've been trying to do is really capture this notion of communication and these sort of chains of interactions that happen. So it's motivated by this sort of crosswalk scenario where we have many different agents, but we can't necessarily have some sort of line of sight or communication between all of them. So we really want to understand sort of how we can capture some behavior between some agents and how that can inform others. All right, so as I mentioned, we'll start with this sort of driver modeling for occlusion inference. So we'll specifically start with looking at this sort of crosswalk setting, since that's sort of a fun example, but then we'll move on to the more general case. But we'll really be focusing in on this idea of occlusion inference. So we're trying to reason about parts of the environment that we can't normally see, or where we're not getting any sort of sensor measurements from that area. All right, so humans are actually very good at some inference. So let's look at a quick example. So this is the clip from that screenshot. So this is a case of a car. It's approaching an intersection. We sort of see this pedestrian pop out. So let's pause it really quick here. So, and if we back up just a little bit, so this is sort of the scene that we're driving through. You can kind of see here, there's a green light. So we do see the case where this driver should not only just proceed through the intersection. We kind of have a odd circumstance though, where we have this car, which is stopped kind of in the middle of the scene. So if you are a human and you're driving here, you think, or you should notice that this is sort of an odd behavior, and this should sort of inform your actions, which is what we see in this case. So the person does actually start slowing down before this pedestrian pops out. So this is sort of this case here. Usually people are pretty good about making these inferences. However, people aren't always good at it. This is actually sort of a pretty critical scenario where we have lots of close calls. There's lots of examples of this on YouTube where people almost hit other agents and whatnot. Actually, this project was inspired by my time as a grad student at Berkeley from personal experience. So, so basically what we're trying to do is try to capture some of these like very good behaviors of people, sort of capture this good intuition so we don't fall subject to some of the poorer decisions that people can make. All right, so again, we'll sort of start with this simple setting. So if we're thinking about how to design this sort of a perception system for this autonomous vehicle here, we can sort of think of a few different ways of how we could handle occlusions. So typically, if there's this sort of region or space that we can't see as an autonomous vehicle, you often will just assume that there's nothing there, or that it is basically all dangerous, that agents are there, there's agents present all the time. So the problem is this tends to lead to sort of this extreme behavior in either the sort of dangerous regime or the cautious one. As we've noted, people are actually pretty good at this. We take sort of these cues and observations all the time. So we want to sort of start thinking about how we can perform occlusion inference similar to the way people do. So specifically, we want to start looking at models of behavior for the agents that we observe, and see if we can start making inferences or draw some conclusions about what might be hidden from our view. So we sort of rephrase this question: can we make improved inferences about the state of the environment, specifically by observing agent behaviors? So again, this is sort of the task of perception. So broadly speaking, perception is this idea of, taking this sensor data and distilling it into some sort of representation. Some folks say you should, or you can operate on the raw sensor data. Generally, I don't think that's recommended. So we want to start processing and take some sort of reasoning about this. Typically what people think about is taking this data and doing basically some sort of semantic reasoning, or mapping this to sort of our semantic notions of what's going on. And I should credit this image to Mobileye, I believe. So typically we take video, we take this sensor data, and we start sort of marking lane regions. We sort of build up this world based on basically our perception of it as people. We sort of have this, like I keep saying, this sort of semantic reasoning and object level reasoning that we basically construct from the sensor data. So typically this is how we do it. It makes a lot of sense for very structured environments. Transportation in general is fairly structured, so it works pretty well. But typically you need sort of one more step to bring this to sort of a navigation type pipeline. So you need to say, okay, if these are where the lane lines are, convert that into something that's useful for my lane keeping controller or my motion planner and whatnot. So an alternative approach, though, is to look at occupancy grids. So occupancy grids are basically a gridded representation of the world, where every place in the world is a cell. These cells are either occupied or free. So what's nice about it is you basically are removing some of the object level reasoning. It's often a little bit more robust to some issues with object detectors and recognition pipelines. So you can kind of look at it more abstract things here. You do lose a lot of information that you can get if you are sort of focused in, but it's like a good backup and is a lot more generalizable and directly passes down to motion planners. The other thing that's really nice about this representation is it directly captures our sort of spaces or our unknown occlusion regions or occluded regions. So in this image here, this is our occupancy grid map. We have the red spots are our known occupied spaces. So this is when basically our radar or LiDAR is telling us that there is an object here. This blue space is our free space. So this is where we know we can drive or move around relatively freely. And all this green space is basically our unknown. So basically the goal of what we want to do here is start sort of filling in some of these pieces here. So I started working on this right after I graduated, actually, but still with some folks at Berkeley, especially Dapo, who's now at Microsoft. But the basic idea is we want to sort of build up this notion of a map. So we take this occupancy grid approach, which basically say we're going to represent this world as this collection of cells. Basically, we say each cell is independent, and this builds up our map. It's a strong assumption, but not too bad in practice. But basically, we're taking this occupancy grid approach, and we can take some relatively standard mapping and inference methods basically to update that. The one thing to note here is that when we're generating this map, it's nominally a function of the states of our vehicle as well as the sensor readings that it's getting. So our goal is to basically augment this inference and add observed actions from these human agents. So we're basically going to treat these observations of these humans maneuvering around us as another sensor input. So we call this people as sensors. And the basic idea is we can basically do a Bayesian update on our map that doesn't include this human behavior and update this with some knowledge of how that human is going to behave. And what's nice about this sort of formulation and update is this is sort of standard practice for mapping. And we just require this, basically this update here. So we want to basically understand the probability of our observed actions given some map. And this is nominally what driver models are trying to do. It says basically given some input, how is the person going to behave? So we just need to build up a driver model that can match basically this insight and sort of match this this representation that we want here. So when we originally started doing this, again, we were looking at this crosswalk scenario. So we collected a bunch of data of basically people approaching or drivers approaching a crosswalk. A person popped out of here or didn't pop out. We basically tried to collect their data so we can get a good understanding of how the people typically behave around crosswalks. We also pulled from a open source data set on vehicle pedestrian interactions called the JAD data set. And we were able to build up these models. And we basically took a very principled approach. So trying to fit nominal models of driving behavior to what we observed, pulled in some things from discrete choice theory to make it happen. But at the end of the day, basically we're trying to come up with these models that related these map representations to the actions. And at the end of the day, we're able to generate some pretty nice maps so we can do some inference on basically the presence of pedestrians. So in this case here, we have the standard grid where we have a lot of occluded space. And here's the part where we're trying to fill this in and improve our inference. And it'll switch over and detect the pedestrian shortly before it actually pops out. All right, so this is sort of a nice example. We showed that this worked pretty well for these crosswalk type scenarios, but it was very, very limited. We were very limited to this relatively simple behavior or a simple scenario. We did require that there were some unimodal behaviors, which isn't normally true. So human behavior in general is very multimodal, meaning that we could have very different reactions to different inputs, or many different inputs could cause the same action. So there's sort of a lot of things that weren't well captured by these sort of initial approaches. And the way we were doing this sort of sequential mapping became very computational taxing, which is common in mapping frameworks, but it was still a challenge. So what we wanted to do is really sort of beef this up. So we really wanted to make sure we could handle more multi-agent interactions. So we started looking deeper into different sensor fusion techniques. I won't go into some of these methods, but we really looked at how we could sort of come up or reconcile conflicting information versus unknown information. So evidential sensor fusion is very good for basically disentangling those factors. And we also wanted to look at sort of these more realistic intersections or scenarios. So what we did is we basically shifted from this very constrained, but what I think is a fun scenario, to a more realistic scenario in the interaction data set. So we have a very sort of crazy cluttered intersection. And we also used some fancier toys to come up with this driver sensor model. So instead of having relatively simple sort of gridded actions and very sort of complete controlled models, we went to something that was much more expressive. So we could come up with sort of more realistic or a model that's more representative of what we see in a broad set of data. So in the more general case here, again, it's the same principle here, but now we're looking at many different observed agents, and there could be a variety of different types of occluded road agents here. One thing that, again, is nice about the occupancy grid approach is you don't necessarily need to know what type of agent is hidden, as long as you have some understanding of how people respond to obstacles in general. So we start, again, trying to directly infer observations of these agent behaviors to the environment ahead. So again, we're really trying to think about what is causing the observations that we're seeing in these drivers, in the drivers that we can observe. We do this for all different drivers. And again, hopefully this can help us infer some of these sort of occluded regions here. As I mentioned, we used a CVAE. So this is a conditional variational autoencoder. And the whole goal of this is that we wanted to learn this function that maps these observed trajectories to these partial maps. The map multiple times is sort of confusing, but these sort of partial environment representations in front of the driver. So these CVAEs are basically this class of generative models that first encode these observations into a latent space. So basically takes in our input, compresses it down, and then it has a decoder that decodes this into some reconstruction of your output. So at a high level, basically what we want to do is we want to have our encoder, which takes in a ground truth map and a observed trajectory during training. And it learns both a prior and a posterior over our latent space here. So during training, we're learning both of these. During inference, we're just basically using this prior. So we'll just use this trajectory as an input to basically infer what sort of mode or what sort of latent variable is present at this moment. And then our decoder basically eats in one of these latent variables and produces our output. And these are all parameterized by neural network parameters here. So to train this whole system, we used, again, this interaction data set. Here we use this kind of crazy intersection here. It was actually coming up or figuring out what data set to use for this problem was a little bit tricky because occlusion inference is not a commonly studied problem these days. I think it's a well-known problem, but not necessarily there are no occlusion data sets. So we actually require things like bird's eye view traffic data sets so we can use this to build our model so we can actually understand sort of the relationship between different drivers. But anyway, so we take this data, we train our model, and then we get this these sorts of modes of behavior. So this is basically the of our latent classes, the decoded maps for them. So you can kind of think of these as sort of template modes or sort of canonical chunks of map that we might see and that cause different driver behaviors here. So there's a few things that are sort of nice about this model. And one of the things that is nice is that it captures the multimodality. So because we get this probability distribution over these modes, we can actually capture some of these sort of multimodal behaviors. So as a example, so if we look at a deceleration maneuver, so if we look at an example of a trajectory that is slowing down, here. So I think intuitively what we would see or what we kind of think about typically is that this means that there is some object right in front of the driver. There's some reason that they're coming to a stop. But it could be also that they see some object sort of off in the distance and they are starting to stop early. So what's nice about having these sort of multiple modes with some sort of likelihood associated with them is we can kind of see the variability in what could cause human behavior. So in this example, the less likely one actually was what happened, but it's very hard to sort of know a priori, right? As another example, this is an example for constant speed. This is a constant speed trajectory. And this example is sort of interesting because we actually don't get much information from the human behavior from just sort of free flow. So in this case, we could have that there is some sort of free flow traffic right in front of the agent. So we're just sort of following normally. Or we could have that they're in sort of free space. And as you can see here, it's basically, we kind of get similar likelihood in these sort of most likely modes of behavior. So it's sort of hard to disentangle or actually come up with a good inference here. All right, okay, so we have this new model sort of that captures again this sort of relationship between what we're observing from an agent and this sort of map in front of the driver that is causing these behaviors, okay? So now we want to fuse all this together. So here's an example from the data set. So we have our sort of ego agent here, which is sort of our pretend autonomous vehicle. It has a number of observed agents that it can see that are causing occlusions, but will also give us some information here. And we can basically fuse everything together. So merge all this information and handle some of the conflicting information to start sort of filling in some of these gaps a little bit more. So let's sort of break this down a little bit. So first, let's just think about what this scenario is. So this scenario here is we have our agent that is waiting to take this right turn. We have this agent here, which is waiting to sort of cut across here. So we have this scenario where we sort of could make a right turn, but we basically can't see that there is a sort of hidden car here. So nominally we would just wait. But for this this sort of key agent here, we see that it is stopped. And from that, we can infer that there's actually an included agent here. So we are able to make a reliable inference about what's going on. So if we were here, we could relatively safely know that it's not okay to turn just yet. However, once this agent starts speeding up, so we see that this agent starts maneuvering, we now see that this space has opened up. So if we were trying to be very efficient, we were excited to sort of get where we're going, we could move in. All right, so this is sort of a cherry-picked example, but there are many others. Another sort of key scenario that we identified was like making U-turns or left turns, so you can predict basically oncoming traffic with pretty high reliability. We also, as sort of one other thing that's, I think, kind of interesting to note is dealing with this fact that we have this multimodal behavior. It's actually not trivial figuring out exactly how to deal with it. But here's an example where we have an agent. So they're just sort of moving straight. We have a few different ways to fill in the map. We also have some other information that's coming in from this agent. So we can start basically looking at the cross product of all of these different agent information. And one of the challenges is you can pick the most likely mode, but it's not necessarily obvious how you should sort of compile all this information. So even though we can, it's a little bit tricky. So sort of dealing with the fact that we now have this capability of understanding all the multimodal stuff, the sort of hard challenge is figuring out exactly what to do with it. Since you do have the case where depending on sort of the, again, sort of the cross of these different modes, you could get that it is sort of free space or that there is some occlusion. So making sure you're robust to sort of some of this extra uncertainty is still a challenge. Okay, so as a sort of quick summary here, so we introduced this paradigm of sort of driver modeling as a sensor model. So again, this is meant to give us this insight to what is causing observed behaviors. The other thing that's kind of nice about this framework or pipeline is we're directly using this occupancy grid map approach, and this lends itself well to this, again, this sort of centrifusion perception pipeline, but also is very nice for downstream tasks. So it's very good for just passing this down to navigation or planning. So it's sort of nice because it combines these different things together. Again, we can now sort of extend some of this early approaches to the work to these multiple agents and capture a lot of this multimodality. And we can demonstrate this. We had real-time performance, so I think we were operating at about 55 Hertz. And we showed this on this sort of complicated and interesting interaction data set here. We have run some real world tests, although we haven't quite finished processing the data. So we did run this experiment on this sort of crosswalk scenario that we talked about before. Running experiments with human agents or with pedestrians is not easy to do. So we were using this pseudo pedestrian here. And we've also been looking at more general crowd navigation scenarios where the sort of impact of your decision is a little bit more free form than you typically get in driving. So looking at a little bit more free, less structured cases as well. So I think I'm pretty close to time here. So I will just very briefly give a quick overview of this other data set, partially just because we've been spending a lot of time on it. So I kind of want to talk about it. But we've been looking a lot at driver attention. So we've been building up this data set that is trying to basically capture all the different influences that could impact driver attention. So basically where people are looking in a field. So we've been looking at basically trying to capture things like attention and driver states, as well as what mode of behavior. So this is some of the first, or one of the first data sets that's really looking at how people's attention changes when you go from autopilot to manual mode or back and forth. So there's been some kind of fun stuff there. We also controlled for distraction. I think I mentioned that, and I won't talk about anything else there. So there's maybe time for some questions. So I'd like to thank my sponsors and my students who did most of the heavy lifting. And if there's some time, I'll take some questions.
Amari? Also, we're clapping. I thought we were asking a question.
I have a question. Hi, Katie. So I'm sort of, you map what the vehicle does in front of you to essentially the occlusion space, which of course is a simplification of reality, right? Sort of the information space is bigger than that. For example, a car could be slowing down because there's nothing occluded in front of them but kids playing on the sidewalk. So it's not a physical occlusion, but it still de facto boils down to something that an effect should still tell me not to drive into the road, for example, but it is not actually an occlusion. So is it that this framework would almost make the car in effect do the right thing? You just sort of use the occlusion map as a proxy for this thing, like kids playing on the sidewalk and not paying attention or something. Or are there key examples where this mapping would lead to the wrong behavior, really?
Yeah, that's a great example, because I think, so one of the things that this model does do is it does capture the fact that I could be slowing down for many different reasons. So there could be a case where there is something in front of me, which is the sort of most likely thing usually, or there is nothing in front of me. And it does capture that. And actually that's, in like this example that I had here. So this is a case where they're slowing down. There's a case where there is an obstacle in front, and a case where there isn't. So, but this sort of generalizes to other things. There could be, and in this scenario, or in scenarios that sort of cause the model to learn this, I should say, maybe there was something sort of that we're not capturing in our map that did cause this behavior. So because the more likely behavior here or reason here is that there is an object, it's quite possible that this would cause the vehicle to slow down, to sort of follow the leader in some sense and slow down. However, there's no guarantee that that's true. And it is, this is one of the things we're actually sort of dealing with now, is there is, you kind of have to tell the agent when it's trying to navigate what is sort of the real obstacles that you're seeing and what is the inferred one. So by fusing everything into this map, you're kind of saying this is all the stuff that is true. But you kind of need to say, like, I think there's an agent here and that should be treated differently. So this is one of the things that we're sort of struggling with, because sometimes it will just think that there is something there when there isn't, or ignore. So I don't know if that exactly answered your question, other than that is one of the faults, but it tends to be better than the extreme where you say it's all bad or it's all good.
Well, I mean, in some sense, right, your point is that whatever you infer here or map you produce, you have to be careful how you translate it into actions. And your argument is that needs to be distinguished, right? So if you had a human controller, you would output pings or warning signals or something, but that not directly lead into actuation, right? More like creating awareness. And of course, if you think of controlled vehicles, then this becomes harder, right? As always. But you could think of sort of a modern vehicle that just has a warning system, right? In addition to the lane ping or something, you just have a careful, there could be an inclusion ping, and then this would be perfectly fine, right?
Exactly.
Any other question?
I had a quick question. I don't want to take up too much time because I know that Sean and Ryan need to start. But well, first, thank you for the great talk. I guess I was curious, do you have any thoughts on maybe where there are ways that urban designers could think about trying to when we redesign the perception in the urban context, that we could try and think of ways to make like the infrastructure more easily accessed by some of these automated systems so they can do these inference problems with higher assurance or more easily?
Let's see, that's a really good question. So depending on how I guess broad this question goes. So once you start having like more like connected infrastructure, actually the need for this problem really sort of goes away. So if you do have like some say intersections where you do have a lot of occlusion, like if there's like a shared sensor or something that's like fixed that can sort of tell you what's around the corner, can provide this extra information, and actually a lot of the challenges sort of go away there. So I think there's some things that again sort of can be fixed if we do have some more of that or some more shared sensing capabilities. I think in general the cases where this seems like it's most useful is where there are sort of these like high occlusion kind of intersection scenarios. And even regardless of thinking about occlusion specifically, these scenarios are one of the more challenging things for autonomous vehicles nowadays. So I think in the design of intersections, just in terms of like the road layout and structure, would make things a lot easier. I hope that sort of answered your question.
No, yeah, for sure. Thank you.
Other question? I think we don't have any more time. Okay, so we can move to the next speaker.